graphs of the exponential function. An exponential is when we have a base, any kind of a base, to a power. Now we want to look at what that looks like if we have an exponential function. What that means is that we are going to have a base of a certain value, and it's going to be to the power of x, where x is going to change every value. So let's plug x into each of the so let's plug x into this equation and find out what the corresponding y value would be. So here I will have y equals 2 to the power of negative 3. 2 to the power of negative 3, that negative means the 2 will go to the bottom, which will result in 1/8. Here that will be negative 2. Here it'll be 2 to the power of negative 2, which will be a quarter. 2 to the power of negative 1 will be a half. 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. And 2 to the power of 3 is 8. So you can see a pattern that is emerging there. Now what we can do is go ahead and try and graph this. Ooh. Try to make the x values as accurate as possible. So I'm going to try and draw up a accurate scale. So that's 1, 2, 3, 1, 2, 3. Well, negative 1, negative 2, and negative 3. And I can see that I need my power to go all the way up to 8. So if I make this 1, 2, 3, 4, or rather, that will be 2, 4, 6, 8. And now all I'm going to do is I'm going to plot each of my points on. So when x is negative 3, I can see that that's 1/8, which is quite a small number. So if here's 1, here would be a half, here would be a quarter, and an eighth would be absolutely tiny over here. When x is negative 2, y is a quarter. So if that is a half there, it will be half of that value. So over here. When x is 1, my y value will be 1/2. When x is 0, my value will be 1. When x is 1, my y value will be 2. When x is 2, my y value is 4. And when x is 3, my y value is 8. And so you can see we're starting to get a bit of a shape of a curve. This value should probably be over there. Now, what happens when this goes on forever? So as x becomes smaller, so as x approaches negative infinity, you will have practiced this before with hyperbolas. What you'll notice is that whenever I put 2 to any very, very small number, so even if I make it 2 to the power of 100, I'm going to get 1 over 2 to the power of 100, which means I'm going to get a very small number, 0.00 something something. So it's going to go on forever, and every time I make that number smaller and smaller, my value is likewise going to get smaller and smaller. The thing is, though, it's never going to reach 0 because 2 to the power of nothing will ever equal 0. So it's going to always approach 0. The y value will approach 0, but it's never going to touch 0. And if you remember, that means that we have a definition where we have an asymptote. So the exponential graph actually has an asymptote at x is equal, at y is equal to 0. Don't forget to label your axes as well as x and y. So here is my general function. We've got a, which is going to be my base, h, which is my left and right translation, and k, which is my up and down movement. Now, because we have an asymptote at x equal to 0, my asymptote will always lie at y is equal to k, and this is what my graph will look like. The intercept will always be at 1 and 0, unless, of course, we apply some sort of translation or dilation. My intercept will always be at 0 and 1, unless, of course, I apply some sort of translation or dilation. Because any base at all to the power of 0 will always equal to 1. So anything that I put will always make it 1. here are some examples of some exponential graphs. You can see that this one is 2 to the power of x, whereas this one is 10 to the power of x. And you can see the graph that is 10 to the power of x just grows a lot more quickly. It's a lot steeper. And that's because when I put 10 to the power of something, the numbers are going to be much larger than when I put 2 to the power of something. So you can see how the bases affect my exponential graph. What we're going to do is compare some of these graphs. So we are asked to sketch each of the followings, and note that we are asked to think about the reflections themselves. So first thing I'm going to do is I'm going to put in my axes. Now, 2 to the power of negative x. What this negative in here does is it requires me to... So what we're going to do in this example is sketch these graphs, but we're going to have a look at the signs and how those negative signs actually affect the graph itself. So we know with our usual graph with 2 to the power of x, when I put in a negative number, so say I put in -2, I get quite a small fraction. So on this side, the numbers are getting smaller. When I put in a positive number, I get a large value. So that means that my numbers are getting larger. So that's why I have small numbers when my x's are negatives and large numbers when my x's are positives. However, if I have a negative in there, that's going to change that all around. So what's going to happen there is if I already have a negative and I put in a negative number, those negatives will cancel out. So I'm going to actually end up with a large number. If I have a positive number, because I don't have a negative there, I'm going to end up with a small number. So what this one is for part A is called a reflection in the y-axis. So it's going to flip so that my large numbers, it's going to grow large in the negatives and grow small in the positives. Now we know that because there's no dilation, my intercept's going to be at 1. So I'll try to graph this as accurately as I can. If we have this as our 8, 6, 4, 2, as we had before, we know that our intercept is going to be at 1. When x is 0, y is 1. And now we're going to have all the values that we had before, but this time they're going to be flipped. So when x is 1, we're going to have y is a half. When x is 2, it'll be a quarter. At 3, it'll be an eighth. At 4, it'll be a 16th, so even smaller. When x is -1, the negatives cancel. So now that's going to be 2, it'll be 4, and it'll be 8. And it'll continue to grow from there. So this will be my exponential graph, which is a little bit hard to draw on the screen. Don't forget that I have my y asymptote here. Y is equal to 0. For part B, you can notice that I've got the negative out the front. What this means is that if I go back to here, any x value that I've put in, I work it out as normal. So when it's negative, my numbers are going to be small. When it's positive, my numbers are going to be large. However, sorry, this should be a 4. However, now we're just going to put a negative out the front because that's what the equation requires us to do. So it'll be my normal graph, which goes like that, except this time it's going to be negative values. So instead of my intercept now being at 1, it'll be at -1 because I flipped it around. When x is 1, I will have my value being -2. When x is 2, it'll be -4. When x is 3, it will be -8. When x is -1, it'll be -1/2, -2 will be -1/4, -3 will be -1/8, -4 will be -1/16, and so on. The asymptote the asymptote the asymptote will remain at x is equal to 0, at y is equal to 0. Finally, for part C, we've got a negative on the outside, which we know is a reflection in the x-axis, and on the inside, which is a reflection in y. So because of all the reasons that we spoke about before, first of all, it'll be reflected downwards, and then it will be reflected in the y-axis. So our intercept will still be at -1, but now with my positive numbers, it will be getting smaller, and with my negative numbers, it will be getting larger. And that's my graph for all of them. That's my graph there. The asymptote remains at y is equal to 0. So that's a little bit confusing, having all graphs at once. Let's just very briefly summarize these reflections. So when we have our normal graph, 2 to the power of x, it will look like this. -2 to the power of x, that is a reflection in the x-axis. 2 to the power of -x is a reflection in the y-axis. And -2 to the power of -x is a reflection in both the x and the y-axis. When we have a graph that looks like this, so our base is between 0 and 1, such as half x, we can rewrite that half as 2 to the power of -x. So this is just simply a reflection in the y-axis, as we've already practiced before. So all this would look like is we've got small numbers at the positives, and it'll grow larger at the negatives because the negatives cancel out. My intercept, though, is still going to be at 0 and 1, because when I plug in x is to the power x is 0, 2 to the power of -0 is the same as 2 to the power of 0, which will be 1. My asymptote remains at y is equal to 0. So for example 12, all of this is requiring us to do is to have a look at what each of these graphs are going to look like according to the dilations or the transformations that they have. So graph A. Graph A. What you can see is it's our regular 2 to the power of x, except now I have a dilation of 3. This doesn't change the shape of it, it doesn't change where it sits on the x-axis. All it changes is how fast it's going to become steeper. So what we should do to show this dilation is first of all find our intercept, but also we can show another point to show the dilation itself. So the asymptote hasn't moved, it's still at y is equal to 0. To find the intercept, all we're going to do is make x equal to 0. So we will have y is equal to 3 times 2 to the power of 0. 2 to the power of 0 is just 1. So we can see that my asymptote is now at 0 and 3 because it's been dilated. There has been a dilation from the x-axis. If you'd like, you can always substitute in another point to show that dilation once again, so that if we make x equal 1, for example, we will have 3 times 2 to the power of 1, which is 6. Part B, that is our -2 to the power of x. Now we've actually already drawn this one. This is just simply a reflection in the x-axis. Our asymptote is the same. Usually our graph goes like this. Now it's just going to go like this. Our intercept will remain at the same point, which is 0, except this time it's the negative version of it, so it will be -1. You can always substitute in another point to show the dilation. So say if we put x is equal to 1, we'll get -2 to the power of 1, which is just -2. For part C, again, we've got a negative, except this time it's on the inside. This one is a reflection in the y-axis. So usually our graph goes like this, except this time it's flipped because the negatives are going to cancel out and affect it. Because this time the negatives will affect it in a different way. So this time we're going to go like this. In terms of our x-intercept, again, because there's no dilations, sorry, our y-intercept, it'll be 0 and 1. If you wanted to check, you just need to make x equals 0, which will be 1. And we can substitute in another point to show the dilation. So that'll be 2 to the power of -1, which is a half. Our asymptote remains in the same position. And those are our x and y axes. For part D, I now have a dilation on the inside there, a dilation from the y-axis. So the only way really to be able to see what happens here is when I substitute in a value. However, there has been no reflections, there has been no translation, so our graph looks the same. It's a positive exponential. It is a positive exponential. But let's see how this affects it. If I make x equal to 0, 3 times 0 is still 0, so I actually get the same y-intercept. But we should always show another point. So if I make x is equal to 1, you'll notice that that's 2 to the power of 3, which is 8. So it's actually grown a lot faster than we had. So it's actually grown a lot faster. So it's actually grown a lot faster than we had before. So this time it's 1 and 8 rather than usually it's 1 and 2. Now we're getting into some translation. So you can see here that my entire graph has been translated upwards by 1. That's really important because usually my asymptote is at y equals 0, except this time it's been lifted and now it's going to be at y is equal to 1. So step number 1, put in your asymptote. Nothing has happened to the actual graph in terms of reflections or dilations, so it's going to look like this. And I can now find my intercept. So when x is equal to 0, I will get y is equal to 2 to the power of 0 plus 1. 2 to the power of 0 is just 1, so I'll get 1 plus 1 is 2. And that's suspected because usually it's at 1, but since my whole graph has been lifted by 1, it's now at 2. Make sure you label your axes. Part F is exactly the same, except you can see now my graph has been dropped by 3. So my asymptote this time is going to be at -3. So there's my asymptote there. Now the question here is whether it passes through the positive section of the x-axis or the negative section. So before I actually draw this on, I'm going to find my intercept. So when x is equal to 0, I'm going to find my y-intercept. So 2 to the power of 0 is going to be 1 minus 3. I'll end up with -2. So my graph will actually pass through here, which means it'll pass on a positive section of the y-axis. At this particular stage, we don't know how to find those intercepts. So for now, you can leave it blank, and in future, we'll learn how to find those intercepts there.